Hello everyone. In today's class, let us start discussion about the spring force. From the Newton's laws of motion, spring force concept we need to discuss, and we will start with the basic one, spring force and spring constant. Now let us start discussion here what is given in the figure. So first spring is there and one end is fixed tightly and other end is fixed to the block, okay, and it is placed at natural length, okay na, means it is not disturbed its length. So this position actually we can call as equilibrium position, okay na. Now here two more diagrams are there which will explain us, that is first let us see, whenever we just pull this block right side, okay, the spring will be stretched. So this is actually spring is stretched condition. Whenever block moved right side through a distance x, and on this position when we leave this one, means we are not applying any force, just when we leave we are not applying any force, then block must be there only, but actually in practical block will move back. Why block is moving back means, whenever we are pulling the block right side, the spring length is going to disturbed, means stretched. So due to that, the force is going to be restored in the spring, and that direction is left side. So that's what, when we leave the block at this position, the block will move back side. This is in the case of stretching. Suppose when we consider the same block here and we just compress the block by x distance. Now we can understand, when we compress and leaving our just when we are removing our external force, whatever the force we have applied. So block won't be in the same position, it will move right side. Again the same scenario, when we just apply the force to compress the spring and block, compress the spring by moving the block left side. So spring length is deformed. So spring force is going to restore. That restoring spring force direction is right side. So the block will move right side. Okay. So this is actually compressed spring position. So in these three cases, this first case where we have discussed, whenever the natural length is there, so no force acted by the spring on the block. Here you can find net force applied by the spring on the block is 0, because length is not disturbed. Natural length will be in the same length. So now when the length is increased or compressed, means stretched or compressed, the spring deformation takes place. Due to that, restoring force produced, and we observe one thing. When we stretch the spring and block right side, spring force producing left side, means restoring left side. And when we compress the block along with the spring, so the spring force restore in right side. So that is for restoring spring force will be always opposite to the direction of motion of the block. Okay. And next, more stretched, this means if we move the block by more amount of distance, suppose we have just stretched the block by x distance and we leave in the position and it move back with some intense, and if we stretch the same block furthermore from this position like 2x distance, and on leaving this position it will go with more intense. What we can understand is, more is the stretching of the spring, then more is the restoring force we can find. The same scenario we can observe here. Okay, when we compress by x and leaving from here it go with some intense, and whenever we compress this one more than x distance, and it will on leaving from this position it will go with some more intense as compared to previous one. Okay, which explains us, more is the compression or stretching, more is the spring force generation. That is the restoring force, means the spring force is directly proportional to length of deformation of the spring. Okay, it is either stretching or compressing, means length of spring increasing or decreasing, means not cutting, just stretching and compressing. Okay, so and direction is what? Opposite. So that's what we use the symbol minus. So on removing the proportionality symbol, we take here constant, that is k, here x minus. So this is actually expression for the spring force, and in this spring force we can say k value is called spring constant or force constant we usually call, and K can be written as from this formula only. So, magnitude of the spring force by length of deformation of the spring. Okay. So, now unit wise we can discuss. Generally in SI system, what is the unit of force? It is actually spring force, but it is a force only, na type of force na. So, definitely unit for force is Newton and for displacement it is meter. In CGS system, its unit is dyne divided by means dyne per centimeter. This is actually unit for the spring constant or spring force. Okay, sorry, spring constant or force constant. Okay, so let us move on to the next slide. Combination of springs, and first of all we just discuss about different types of combinations here. So, first one is springs connected in series manner. So, series connection is nothing but end-to-end connection is called series combination. Okay. So, let us see, one spring is here K1 spring constant and one more spring whose constant is K2, and these are connected end to end such that one end of the second spring is connected rigidly and other end is connected to spring 1 and spring 1 other end is connected to block. Okay. Now, here it is applying some force F, it is pulling right side. Okay. So, you just understand that one concept. Whenever we are pulling right side with applying some force, okay. So, we will just a concept we can make clarity here. First, F equal to Kx is the formula. In this combination or whatever the most of the combination questions, out of 3 parameters, 2 will be variable, 1 will be constant. We will find the same scenario here. Okay. Whenever we apply the force on this block, the same force will be transmitted through the springs. Means the spring 1 experience the force F only, and second one spring 2 is also experience the same force only, which means the force whatever that restore in the spring 1 and spring 2, we can take it as what F only. Okay. Then what are the parameters are going to change? Here changing parameters are spring constant K1, K2 different, and here length of deformation means first string might be deformed different length and second spring will be deformed different length. Okay. So, from the concept of F equal to Kx, generally we can write this is F equal to Kx. Okay. From this one we can write down X equal to F by K. So, minus we can write. So, now consider, suppose block is moved by a distance y, here as per the diagram y distance it is moved. Then the spring 1 deformed by y1 and spring 2 deformed by y2. So, this deformation will be add up in the displacement of block. That is, from the displacement of the block we can take y is equal to y1 plus y2, like this we can write. So, that is actually displacement. This is also been we can indicate in terms of y. So, y is actually 2 springs are replaced and effective spring is placed in the place of 2 springs whose spring constant is equivalent of spring 1 and spring 2. Okay. So, now here we can write, and that is also applied by how much force here? F only. So, we can write here F by K equivalent is equal to, here again F only, because I just now told F will be same in the springs whenever they are connected in series manner, because displacements are different here. Okay. So, F by K1 for the first spring, next minus F by K2. Since forces are same and minus also getting cancelled, now we can make K equivalent 1 by K equivalent equal to 1 by K1 plus 1 by K2. That is K equivalent on simplifying further, we can make K1 K2 upon K1 plus K2. This is the effective force constant or spring constant in the combination of a springs in series. Okay na? So, now let us move on to the next one. Springs in parallel combination. Parallel combination modes are 2 types here. This is one type and this is second type. okay, and many students they felt in this combination it is connected in series, but I will explain how to find out series and parallel. Just wait for that situation here. So now this spring and this spring 1, spring 2 are connected, first end of the both the spring connected to rigid support, and second end of the springs are connected to the block. Such a combination is called parallel combination. So we are discussing now springs in parallel, right? So here these springs are connected to the block and the block is pulled with some force F. Whenever the block is pulled with some force F, the force will be divided into two parts, like F1 acting on the first spring and F2 acting on the second spring. So in this case, force is variable and displacement must be same. So that is, suppose if I move this block by displacement y, then spring 1 and spring 2 must be moved in same displacement. This is actually key point for identification of parallel combination. Okay na? So you can just understand the same point here. Whenever I compress this one by y displacement, then here how much length expanded means stretched y only. Next, whenever we compress this side y length, then the spring will be extended or stretched by y. So when the displacement of the block will be just moved right side or left side, the deformation of the spring lengths are same on either side, but one is compressing, one is stretching. So such a combination is we can discuss as parallel combination. So here we can say from the formula of spring, Fs equal to minus kx, or just we can write minus ky. Here displacement will be same, so we can just make as force is going to be splitting. So we can add up here F equal to F1 plus F2. F1 is the force acting on spring 1 and F2 is the force acting on spring 2 and F is the force acting on block. So now these springs are removed, only one effective spring is fixed and whose K equivalent is equivalent for both the springs. So in that case, that spring also should move by displacement y only on the application of force F. So we can write here K equivalent into y. So minus I am writing here because F equal to minus kx or minus ky. So minus k1 y plus minus k2 y. Minus minus cancel, y cancel. So K equivalent equals to K1 plus K2. This is effective spring constant in the parallel combination. Okay. So next we will see some questions here. Okay na? Some numericals we will just solve based on the water spring concept here, right? So this is actually not a regular model question. This question is like based on constraint relation based. On applying a force F at point P, here point P is there and on point P, F is the force applied and is displaced vertically down, means it is displacing by applying force F by y meters or y centimeters, y meters only we can write, from equilibrium position. Actually this is in the equilibrium position whenever it is pulled down by y distance, okay, from the equilibrium position. Then find the force F in terms of the force constant K of the spring and displacement y for the case A and B. Either case they are asking. Here one spring is there, spring constant is K, and now this point is actually P is in equilibrium initially and now it is pulled downward, okay na. Whenever it is pulled downward from the equilibrium position through a distance y, they are asking us to find out what is this magnitude of F in terms of K and y for the situation shown here, both the cases like A and B. So let us start by first question, okay na, means figure A. This is actually rigid support and here we have a pulley and here it is spring and it is again rigid support and this is point and from here the force is applied, okay na. So now it is moved by distance y, okay. Whenever it is pulled down through a distance y, due to constraint relation we can assume, suppose it is moved by y1, okay. Need to be give clarity, this is y, this is y1. both are not same. Okay na? And whenever it is disturbed by y1, there is a spring force produced in the spring as Fs. Okay. Now we will make a relation here, that is constraint relations we can take. So here is the spring and here is the pulley, and here are the two parts of the rope of the pulley, rope passed over the pulley connected from bottom end. So we can take 2 points on the rope, and downward it is actually acting F force, and the same force will be transmit here, downward F only acts. And from through this point, whenever it is pulled down, means by this force whenever we pull down, pulley also move down, then this spring will be deformed. So due to that, restoring force or spring force produces upward. Okay. Now in this equilibrium condition, Fs must be equal to 2F. We will write the same point here. Fs equal to 2F. This is the first relation we can get. Okay. And second constraint relation we follow. That is what here by application of F force, it is moved through a distance y. And we have discussed many questions based on the work tension method, tension force by using work and tension method we usually call. So what is the force applied on the point here F, and it is moving downward only, F into y, positive work, and here spring force upward and downward y1. So we can write Fs y1 equal to 0. The point on the spring moving through this much y1 distance. Now Fy equal to Fs y1. Next here Fs equal to how much we have? 2F. Okay na? So we can just make here y equal to Fs equal to how much we got? 2F. And here y1. So F cancel, y is equals to 2y1, which means the displacement of the particle on the spring is y1, then point P displaced through 2 times of y1. This actually gives constraint relation we obtain from constraint relation. Okay. Now we can use the same relation to obtain, and by application of this one, and we can make the solving of what F value. First they are asking capital F value in terms of K and Y, means K should come from what? Spring force, means we need to solve spring force also. Okay na? Let us take here from the same relation we can continue, that is Fs means we can take K y1 equal to 2 times of F. Okay. And now y1 equals to, from this equation y1 is equal to y upon 2. Okay, y1 equals to y upon 2 we will get from this equation. So we can put here k into y by 2 equals to 2f, and on simplifying f equals to k into y by 4 or k by 4 into y. So this is actually we can take what is the force acting on the point P in terms of k and y. Okay na? So in this way we can solve that by using constraint relation. Okay, major application is constraint relation we have follow here. Okay, next second question. Here F is downward and here one point is there, on this point F is applied and making stretching through distance y. We will find the F value in terms of k and y. We will see in the next slide. This is the scenario here, whatever given in the question, and this is F, okay, and it is being moved by y distance as per given in the question. Suppose and a pulley will disturb and move downward. Due to downward motion of pulley, spring force acts upward and it is been moving downward by y1. Again y and y1 are not same, okay, and free body diagram we can follow. We can just draw here free body diagram, and here upward how much force act? Fs, and the same string part connected to this one also, and here also how much force act? Fs. and through the pulley downward force how much here? F. Through the pulley downward force F. So by balancing here, F equals to, we can write 2 times of Fs. This is first one. Okay. Second one, constraint relation we can follow. That is F applied and moving downward. So work tension method, F into Y. Next, Fs upward, Y1 downward. Again work done is minus. We will write minus Fs Y1 equal to 0. That is Fy equal to Fs Y1. So we can take F equals to 2Fs only, na? We can put here, that is 2Fsy equal to Fsy1. Fs cancel, 2y equals to y1. Okay, this is constraint relation. So let us assume from this equation only, from this force equation only. So let us take this is equation number 1. So from equation 1, what we have? F equal to 2 times of Fs. Okay, and what we know, force, spring force equal to K times of Y, Y1 here. So we need to write Y1. Okay, na? Now 2 times of K into Y1. Y1 equal to how much we have? 2y. So this is equation number 2. We can write from equation number 2. That is finally 2 to the 4. We can write 4ky. So this is F value in terms of K and Y. Here we can write 4ky. Okay. We use again constraint relation and net force equation, and we just to simplifying we get the answer. Okay, na? Next. 2 blocks are connected by spring. Here this is spring and 2 blocks are connected as shown. The combination is suspended at rest. Okay, na? And from a string attached to the ceiling. Actually this is string, rope. From the ceiling it is been suspended. Now the string breaks suddenly. So this string means rope, cutting or just break suddenly suppose. Then immediately after the string breaks, what is the initial downward acceleration of the upper block of mass 2m? Okay, this sort of questions we need to solve before breaking the string and after breaking the string. Okay, so first of all, let us start with the free body diagram here. That is here 2m mass, okay, and here m mass. Here in this one spring force. Okay, na? So upward there is a string connected, rope connected. Due to string we can find tension is upward. Okay, and next to 2m g is weight force of the block downward. Okay, na? So now the spring will be exert some force here. That force will be taken as kx downward only. Okay, na? Now on this block, M block here. M block is connected with what? Spring. So here spring force will be exerted upward. This is Kx, and downward force will be mg. And this is in equilibrium, means before breaking the string it is in equilibrium. So we can write upward force equal to downward force. From this condition, what we write here? Kx equal to mg. Okay. Now from this situation, T equal to Kx plus 2 mg. This scenario we can make. Okay, na? But Kx equal to how much? Mg only, na? So from this equation we can re-alter this one. That is T equal to, from this equation and from this equation, Kx value how much we have here? Mg. So we are putting here mg plus 2 mg. So total tension is how much we got? 3 mg. This much tension is going to be exerting on the 2m block. Now suddenly the string is cut, means suddenly string breaked or rope breaked. Then after cutting we can understand here downward force is how much? 2 mg, and downward force is how much here? Spring force. Okay, so we can take Now upward force, actually initially how much we have? Tension, but now tension become 0 after braking. And one point you need to understand, after braking immediately they are asking in the question, you can see this is immediately after the string breaks. In that span of time, spring force does not alter, spring force will be same. So now whatever the spring force was earlier is there, the same spring force is going to be act. Now we can check here, Kx equal to how much we have earlier? Mg. The same force is going to act here, Fs value as mg, but upward force is what? 0. Then total force acting on the 2m black is downward. So here it is 2m mass. So it is accelerate downward. So downward net force Fs plus 2mg equal to 2ma. Okay. Now Fs value how much we got in the earlier case? The same force acts here, mg plus 2mg equal to 2ma. So here we can simplify, this is 3mg equal to 2ma, mm cancel, a equal to 3g by 2. This is the acceleration of the 2m block downward direction, because net force on this one is, both the forces are acting downward. So that we can find its acceleration is downward. Okay, na? So this is what we got. Next, okay, this is the answer for the question, because they asked initial downward acceleration of the block, upper block of mass 2m. Okay, na? So in this case we found 2m mass acceleration, it is moving downward. Okay, one point you need to remember in the question, what is that? Whenever breaking of a string suddenly, immediately after the breaking, the spring force does not alter. That will be remain same for fraction of time. Okay, in that fraction of time we got this answer. Next, here one question, find the acceleration of 3 kg mass when acceleration of 2 kg mass is 2 meter per second as shown in the figure. Okay, so we will redraw the diagram here. This is actually 3 kg mass and it is being applied by spring force here, and here this is 2 kg and right side 10, and its acceleration is 2 meter per second square, and back side is what? Spring force. Okay, now spring force equal and opposites as a system, as a total system also we can solve this question, but separate also we can solve. Okay, na? So this is actually free body diagram. Now for 2 kg block, what we get? 10 minus Fs equal to 2 into 2. So 10 minus Fs equal to 4, Fs equal to 10 minus 4, which is 6 Newton spring force we got. Okay. Now we can go with the next concept here. This is what a 3 kg block, and what is the force acting on 3 kg block? Fs only the force acting on 3 kg block, because backside no force is there. So Fs equal to 3 into a. Fs value how much got? 6. So 6 equal to 3 into a. Acceleration of the block is 2 meter per second square only here also. And this is one method as individual. If we suppose assume all as a system, okay na? Suppose we can take all as a system. This is 3 and here Fs and it is 2, here Fs, and all as a system means equal force and opposite direction. So we can ignore the what here for spring force. Now they will move with the same acceleration generally. So how can we solve? 3 plus 2 into acceleration equal to 10 Newton, 5a equal to 10, acceleration equal to 2. Like this we can solve. So this is not mostly appropriate general cases, because they will involve the question in next lesson as friction also. So you better you follow this one only. Okay na? Let us see next. Here two blocks of masses m1 and m2 are in equilibrium. Here this is m1 and this is m2, and hangs from the fixed smooth pulley by an inextensible string that is fitted with a light spring. Here this is spring, of constant stiffness constant K, neglecting friction and mass of the string. Here string mass also not there, this is actually string, okay na. Now find the acceleration of the body just after the string S is cut. So here just after the string is cut, what are the accelerations are being acting. So let us start discussion here first. Here left side, what is going to act through the string, we can find here it is tension, okay, and here what we can find, this is spring force. And suppose we can assume this is T, and we can assume here as a point, one point on the string, and for the point here this is Fs and right side T1, okay. Suppose you can assume this is only T1 and you can take it as T2 this one, because it is following to M2 block, no confuse, right. And here from this point upward direction we have T2 and downward how much, M2G, right. So it is in equilibrium, string is not cut initially. So now we can take T2 equals to how much as per the diagram, T2 equals to M2G, and this point is also not moving right side or left side, then T2 is also equal to what we can write, Fs. This is second point, T2 equals to Fs, okay. Now here Fs can be written as here Fs equal to M2G, because T2 equal to Fs only la. Now this Fs is going to acting on M1, and M1 is being exerted by T1 tension left side, and also we can write T1 equals to Fs, means T1 and T2 equals to spring force come, right. So these are the net force equations initially. And what happens immediately after the string is breaking, okay. You can see here, whenever we break the string, which force is going to become 0, T1, okay na. So we can find here, after string is breaking, here M1 and it is being exerted by spring force, okay na. So we can write down spring force equal to M1 A1, suppose A1 I am writing. Now spring force value how much we got from this equation, M2G. So that is we can make M2G equal to M1 A1. So A1 equal to M2 by M1 into G. This is the acceleration of the block 1. Next, as T2 equals to still spring force only there, and that spring force value and T2 equal to M2G also there, means second block. So now second block we can write down downward force M2G, okay, and this T2 is connected with the spring, means spring is not altered, so T2 also not altered. So T2 value, upward value how much we got in the earlier case, M2G only. So we can write upward force and downward forces are same, then F net on the M2 must be 0, then acceleration of the second block must be 0. That second block will be at rest, okay na. So next one, a block of mass 20 kg suspended through two light spring balances as shown in the figure. Calculate the reading of spring balance 1 and spring balance 2. You can find here 20 kg mass suspended by two spring balances, and you can find this concept from the series combination. You can find, see here, end-to-end combination, okay na. So when end-to-end combination is called series, just we know discussed here. So in this case, the force must be equal in both the springs. We have discussed the same point in spring combination in series model, okay na. So whatever the force it can be felt is 20 kg force, okay. Then the same force will be exerted in the spring balance 1, and it is also pull this with the same force for the spring, sorry, this is spring balance 2, and it is also pull with the same force on spring balance 1. So only key point to solve the question is how spring balances are connected. First one is series. Now go back to concept of series combination. In series combination, the force must be same in the both the springs. So here whatever the force is exerted by the block, that force will be exerted on two spring balances here. So both spring balances must show mass must be 20 kg and if they will be or they will ask you to find weight force, then 20g means 20 into 10 or 9.8 Newton forces. Generally we used to find generally what mass of the block, okay, but here what they are asking, spring balances and reading of the spring balance they are asking. So first balance, second balance, both will show how much value, 20 kg force, okay, 20 kg. So here you can find this is the spring 1, next to this is the spring 2, and it is connected with 20 kg, and here whatever the force is exerted, that is 20 into 9.8, otherwise approximately we can write 20 into 10, whatever you can take, okay na, it comes 196, it comes 200. So here this comes as newtons, and the same force is going to be shown by the R exerted on the spring balance 2 and the same force exerted on spring balance 1. So that's what the reading of this balance must be 20 kg and the reading of this balance must be 20 kg. Key concept to solve the question is how the spring balances are connected series. Then force must be same in both the springs. Okay na? This is what we can solve the question by application of concept of springs connected in series. Okay, thank you.